Hey guys, DMS here. Today I have with me my friend Jose, who is a research assistant and a master's student, and you also said Smart City Developer.
Yes.
Very interesting title, working with a lot of really cool projects that honestly go way over my head, but I'm here today to learn about them and so that you guys can too. Jose, tell me a little bit about what it is that you do.
Sure. So I'm actually based out of Chattanooga, Tennessee. So if you haven't heard or don't know, we're actually building up a smart city. So we're actually trying to build up we like to call it a smart corridor just because it's only for a specific stretch, but we're essentially trying to put together a sort of collaboration base out of Tennessee, or out of Chattanooga. So the way it works is we have about a mile of Martin Luther King Boulevard, which is essentially kind of down the heart of Chattanooga's downtown area. Mm-hmm. And so we have, I want to say, 7 different intersections throughout there that we currently have cameras on and a bunch of sensors. So the idea is we want to make an open platform for developers to come in and say, hey, we have this new sensor that we'd like to deploy, but we don't have a smart city. Can we use yours?
Okay.
Or if you have some algorithm,
ground.
Exactly, or if you have some algorithm that requires a lot of good smart city data and you need it, mm-hmm. you can come to us and we can provide you with the data. So we're trying to build it in a way that's scalable and also like an open platform for people to either come and take data from us or to provide us a new set of data from their sensors and mm-hmm. also read from them. So we've built up this whole like really open architecture that has, individualized dashboards, and mm-hmm. So from the software side, you can go and see just your data if you're not from one of us, and we can come and see all of the everything. So again, each one of we have, I think it's 16 different poles that mm-hmm. we'll have access to. And so the way they'll work is the ones that are at intersections that already have power routed to them will use power. We use EP5's fiber optic network, which is a 10 gigabit per second backplane, so it's actually really fast. Yeah, and really viable for real-time data, which is what we try to produce.
Okay.
So we stay within about half of a second of delay from point to end with some of the stuff that I do, so it's
probably
actually
over considerable distance.
Right, exactly. So it's rather real time, especially for the things that you can use it for from there. So on each one of these on each one of the poles we have any variety of air quality sensors. We have a lot of wireless network sensing, so not only do we provide wireless networks that you can interface with if you had, like, say, a smart car that was mm-hmm. interfacing with the infrastructure. We call that V2I, vehicle to infrastructure.
Okay.
But you could also, for example, analyze network activity nearby. What kind of frequencies are coming through here? Are we getting a lot of 50 gigahertz, 60 gigahertz, or how much interference are we getting? So mm-hmm. we're doing that through SDR and DSRC. And that's kind of one of our coming up work in progress type things.
Real quick, just touching on that, or at the very beginning of this, so smart city in general.
Yeah.
When I think of that kind of terminology, I think of like a smart car or I say smart car, like the self-driving cars.
Sure.
Or like the smart homes, like
mm-hmm.
the Google Homes and the Philips Hue lights and all that stuff. Right. What does smart city mean for a city exactly?
It means a lot of things, and honestly, that kind of goes from city to city. And there's mm-hmm. a lot of implementations that you can do that aren't ever alike that are still definable as a smart city. So our definition of a smart city is a city in which you can have technology that can assist the occupants of the city. So you have these things that don't require someone or something to do the analysis for you. You have the city do the work for you. So, for example, imagine waking up in the morning, routing out, okay, I'm going to leave at 7 in the morning mm-hmm. for work, and I have to go down this street. Imagine instead of having to go to Google Maps, you just go out to your car, and your car interfaces with the infrastructure, and the infrastructure tells it, hey, this one street is really busy today, you should take another street. So
you could essentially, with enough cars in a network, you could like relieve congestion and things like that.
Exactly. I mean, there's so much, you can do a lot of load balancing for traffic. You can also do, one of my previous papers that I wrote for a class was traffic mitigation in the event of an emergency vehicle. Because if you have an emergency vehicle fly through an intersection, and if the lights were green at red for it as it's mm-hmm. flying through the intersection, you want to change it so that, first of all, least people are in danger of that mm-hmm. vehicle, so no one's going. But then you're still going to have an inevitable backup whenever that happens. So you're going to have these vehicles that you're going to need to try to mitigate the backup. So again, and that's another definition for smart city, is a city that has maybe smart traffic lights and lightweight computing on each pole. So it really just depends. So
that seems like it requires a little bit of giving this system the ability to have somewhat of a, I guess, a system for foresight.
Right,
to an extent.
Yeah, prediction is always that's what neural networks are for. That's what artificial neural networks, especially convolutional neural networks or MLP, is great for prediction, like that kind of stuff, where you can go through and say, here's what we've had in the past, and here was the output. Here's what we have now. What's the output going to be?
Okay.
So you can kind of go through
machine
and
learning.
say, exactly. So that's all parts of machine learning that could really help.
That's an alarm clock.
Yes, it is. It seems to be working. It worked. So there's a lot of opportunity to make things particularly fantastic with this infrastructure. So we have cameras, we have audio sensors, we have lightweight edge computing. So we have NVIDIA Jetsons. I don't know if you've ever heard of them. And we have Raspberry Pis, which everyone has heard of by now.
Right.
The NVIDIA Jetson is fascinating. It's the developer's kit board is about this big, and it looks like a standard motherboard.
Okay.
Except it runs an NVIDIA Tegra GPU on board.
Okay, so probably a lot more powerful than a Raspberry Pi.
It's great, because if you don't know, machine learning thrives off of CUDA on an NVIDIA GPU.
Okay.
So if you're putting the pieces together now, we have an NVIDIA GPU. We have this small little board out on the edge that plugs in, and it has everything else you need. It actually runs Ubuntu.
So you're looking at basically self-contained machine learning.
Yeah, self-contained machine learning right there at the pole. Like, you can't get any less latency than right there at the pole.
Right.
So we have that, which we've yet to tap into, because since it's not on the x86 architecture, a lot of libraries for Python and for machine learning have not yet been ported to it, because it is using ARM.
Okay.
So
I keep hearing ARM more and more and more. It seems like everyone's kind of moving in that direction.
Yeah, I mean, I figure soon enough everything that we need will be on ARM, and it's just going to be another one of those things we laugh at. But I mean, if you look back at the first Windows RT tablet that everyone thought was going to go somewhere, and it went nowhere.
Right.
I would love to see that thing fly again in a few years, where it's just like, oh yeah, you remember that old Windows RT tablet? I'm running, video games on it now, or
the big
whatever.
limitation of that was just the app support, I think.
Yeah, for real, because that way you could only get through the store, because you only could get, these ARM-based programs. So,
well, you see companies like Apple doing that now. They're everything's running through an app store, and they're talking about moving away from Intel towards ARM CPUs of their own design. And they're already doing with their phones.
Right. And while that does sound like, a lot of these things sound scary to people who don't know anything about programming, but my undergraduate was actually in software design, so I know a lot about how that works. And the coolest thing about it is, while this sounds frightening, unless you're doing anything at the core level that directly involves the CPU, the compiler handles it all for you. So all you really need to do, unless you're, again, doing some very invasive CPU-level stuff, CPU-bound stuff, all you need to do is update your compiler, compile it with ARM parameters, and you're good to go. Your code may not need to change at all. Now, this does vary from place to place, and how long it takes for a compiler to update is inevitably...
Adobe.
Yeah, right, exactly. So you just never know. But, going back to the smart city, having all this edge computing and trying to figure out how to do these things, we're still figuring it out, because there's no textbook definition for a smart city as far as architecture and infrastructure and how to do it. So there's very few. I mean, I think there's maybe, I could be wrong on this, I haven't looked in a long time, I think there's maybe 3 other ones in the US, and then there's one really great one in Europe.
Okay.
So,
you guys are really on the kind of the bleeding edge of something here, then.
Right, and I mean, you do hear that Chattanooga is considered the Silicon Valley of the South, so we're really just kind of pushing more and more and more towards that belief of, here's these things that we have that have been opened up by having this blazing fast internet. Let's use it for something other than torrenting crap at the speed of light, you know?
Or loading YouTube videos in 4K.
Right, or being able to download new ISOs in no time. Like, it's...
I would like to have upload speeds like that here. It takes quite a while to upload episodes like this.
Yeah, see, in my episodes for my old stuff that I used to do, it takes like 3 minutes, for a 7 gig file.
I would love that.
Yeah, it's pretty great. So, but you can use that for such greatness as well. So one of the things that we've done is with these cameras... Oh, actually, let me rewind.
Okay.
So you hear all this stuff about all this data. You've got audio sensors, which, to break it down, is a microphone.
Right.
You've got cameras. You've got all this stuff that sounds like Big Brother and like Facebook type watching you everywhere you go
right now.
Yeah. No, we don't do that. We've actually made an open promise to the community, and we mean this. Like, we actually have a lawyer who makes sure that we keep on top of stuff, and we have NDAs for things. We have made a promise to the community that we will not release any personal data. We will not store any personal data. We do not have any personal data. All we have is anonymized data. Everything we ever share with anyone is stripped away, and none of it is ever recorded. Only the numbers, only the data.
Okay.
So I just kind of want to clarify there. So one of the implementations that we've done with this that actually really shows how numbers can be powerful is we've created an algorithm that uses a machine learning model that is in progress as far as optimization. It still has some work to be done, called YOLO, which is... we all know it for you only live once, but it's actually you only look once. So the way that it works is you have a lot of convolutional neural networks that work by scanning the image multiple times, which adds delay. That's why you can't really use CNNs in real time as far as seeing, fantastic results at 60 FPS. Like, you just don't see that. But that's roughly what YOLO does, because it only scans the image one time. That's where the look once part comes from.
Okay.
So you trade off some accuracy for FPS. But the nice thing is we're using it for real-time detection and tracking. So there is a difference between detection and tracking. Detection is just where you give it either a frame or a video, which a video is just frames with a delay between showing each one. So you give it a frame, and it comes back and it says, here are the hitboxes and the detected types and how certain that I am that it is that detected type. And so you can then draw those over with, boxes and labels and text and whatever. But when you hand it the next frame, in the case of a video, it doesn't have any object permanence. It doesn't know that the same car you detected last frame is the same car this frame. It does not know. It starts from scratch.
Okay.
So that makes taking data and attaching it to objects very difficult because there is no object permanence in this situation.
How do you work around that?
That's where the tracking comes in. So what essentially gets done is we're using a tracker so that our objects get detected first. Those detections get sent to the tracker, and the tracker keeps a snippet, like the image itself, of the box that it got detract from, and it stores it so that the next time it gets one, it will go through and try to reassociate them together based on the distance. Like, so essentially, if you think of an image as a matrix, right? So it's a 2x2 grid filled with numbers.
Yeah.
And it's really easy to visualize if you think grayscale image. So you have a 2x2. You don't have a third dimension for colors. It's just 2x2
you just have, like,
and
white
0
to
to
black.
255 for white to black, or black to white. So if you look at it that way, what it does is it actually does a past to current comparison to see how different the values in the matrix are and how different the shape of the matrix is. And if they fall within some threshold, then they say, okay, this is the same object. So
Looking
with that,
for a pattern, basically.
Exactly. So with that, it can detect this pattern. It's called you can do it with what's called a Kalman box filter.
Okay.
So it will essentially reassociate past image to current or past object to current object. So with that, I can get super valuable information like where was the object located at every single time it got tracked, and give me a timestamp associated with each one of those locations. So I know exactly when it was where. With that, you can drop a lot of things like velocity.
I was to say how fast it's going.
And with velocity, you can determine traffic trends.
Okay.
So you can say,
I
okay,
can see that kind of coming together
you
now.
can say, okay, this object sat through this intersection and it took it 30 minutes. It sat in one spot for a really long time. But I have to do stuff on my side because we send this all to a database. So if we have 30 spots or 30 minutes at 30 frames per second, which is what we run at, and it's getting that detection every single time, you're building up a giant amount of data for it to just say, yeah, it was in this one spot for 30 minutes. So I'm doing some generalization, if you will, where I essentially say, okay, instead of keeping track each time, if it hasn't moved by some certain threshold amount, just ignore that one until it gets to one that has moved a lot. So you'll basically still have timestamp from where it was first found, and then if it stayed still, then it won't show any new ones until it moves a lot, and then you'll have a timestamp for that, so you'll know how long it stayed still as well. Still, you're not really losing any data; you're just simplifying it. So you can do some trends as far as traffic analysis to see, if the object was here for less than some ridiculous threshold, like 30 minutes, because these cameras don't have a very wide focus angle. So we have some variable focus and wide focus, and so the wide ones still can't do much more than maybe from one corner of the intersection to the other. So realistically, traffic should never be that bad unless there's maybe a tragic wreck.
Right.
So with this data, we can take those kinds of trends, we can see what kind of object is it, we wrap it up, and we send it to our database, which is, it's not really a typical database. We want, we're using this, it's not really a database, it's more of a data share. It's on a publish-subscribe system. It's called Apache Kafka. So the way it works is that you send something in, and if you send something in, you are considered a publisher. And if you want something from it, you're considered a subscriber. And so the way it works is it actually uses your machine's cache to store these values. So it's actually super, super fast and is more or less real time for people who are subscribed to it or publishing to it.
Right.
Versus a normal database, which is like, oh, where should I put this? I think this is fine. Then it's got to seek to the hard disk to figure out, is this where I want to put it? It's a mess. So from there, we can do a lot of really powerful things like graphing. We can use... we can index, and then from the indexer we can graph, or we can make dashboards using Grafana or Kibana, which is what we do. And those dashboards, again, can be customized and individualized for the people who we are collaborating with to only include their sensor data.
So there's a big focus on, it seems like across the board, a big focus on low latency real-time information.
Exactly, but with collaboration, again. So if someone has some new sensor, let's say they've got some new... I was going to say LiDAR, but Elon Musk says LiDAR's dumb, so I'm going to say supersonic. So if they have a sonic sensor and they want to test it to see, can we, before we stick this on a car or something, can we tell other cars without having to put it on a car? They could slap it up on our infrastructure, put it up somewhere on a pole, and point it to cars or where cars would pass and see if it works, and we can send them their data to them. And
so
they could be based out of Germany.
For all kinds of things, even things that aren't going to be specifically used in cities.
Right, exactly. Ideally it would be used for cities, but if it's something that could be applied to the test bed, then of course we'll take it.
Another element of the city, the car being an element also.
Exactly, and that's how we're kind of trying to consider it. So what gets sent to the database is essentially the original time the object was shown, the object's label, like car, truck, bus, etc., the ID it was given, and that set of locations with the timestamp. That's all we get from the video, and as soon as the video is streamed, after that video is streamed, if the next one, or after that frame is streamed, when the next one comes in, the last one gets deleted. So we don't even buffer, we don't store. It's here and then it's gone.
Right, it's not a security camera, it's literally a computer that's generating data out of this.
Exactly. So for the sake of privacy, again, we don't want to have anything to do with anyone's personal lives. We just are here for data to better your life, if that makes anything sense. Yeah. So, and it's generated a lot of very interesting and very useful graphics as far as seeing traffic trends and how they dip. And alongside it, I mentioned we have air quality sensors. We're also getting graphs for those.
I was wondering about that. Things like what kind of uses do you see for air quality or for microphones?
We have actually already gotten into the air quality because we get in these readings and we put them through Elasticsearch. Well, they go again through the entire stack. So they go to Kafka, then they go to Elasticsearch, then they go to Kibana and Grafana. So with Grafana, we can graph. So we've seen an almost inverse trend in a high number of cars versus a low level of pollution, as in little pollution. So it's really strange, but it's also leaving us another question that can be solved with research. Why does it increase at times when there are no cars or fewer cars? Like, what is the cause of this? We believe
air movement, all kinds of other things.
Right, we're tempted to believe air movement, weather, we think. So we're considering one of our upcoming projects to be Dark Sky, using Dark Sky, which is historic weather data database for a location, to see what was the weather for this time where the air quality was this, and see if we can put together some sort of correlation and maybe even a predictor, so we can say, like, imagine for a big city like in Korea or Japan where the air quality is bad. being able to predict when the air quality is going to be bad based off
Right.
what the predictive weather is going to be. And being able to say, okay, well, it's going to be a thunderstorm, and also you're not going to be able to breathe in this without any sort of, safety or
Right.
mask.
All the cities that have like massive smog.
Exactly. So, or you can say the weather's going to be bad, and there's this. We need to amp up our public transportation to make it easier for people to not drive. Things like that that can really, really, really help the city. Going to the audio sensors, there's a library slash machine learning implementation called Sonic, which is Sound of New York City.
Okay.
It's produced by NYU. It's one of their research projects as well. And what it does is it takes in sound waves, converts them to video. I don't know why. Converts them to an image.
Okay.
And then it runs a CNN on the image to determine what kind of sound it was. So with this, we can determine amounts and sources of noise pollution. We can, that's really the biggest one off the top of my head, but again, we can also associate, is the noise pollution from certain types of things like construction, and can we see this construction affiliation show maybe a slowdown in traffic as well? So there's a lot of things that we could do with that we can kind of, again, do predictive analysis with, okay, there's a lot of noise pollution this morning from construction. There's going to be a lot of traffic, and we can predict how much traffic or where.
So all kinds of other things we wouldn't normally think that can contribute to other trends.
Exactly. And so the crazy thing to think about is we're using machine learning to get this data, but we can also still use machine learning on the data we get. So it's almost like an in and out with machine learning. It's crazy, but we're just taking raw sensor data, turning into important data that could also be used with machine learning to do predictions, or if we get a lot of data, like for example, the purple air. The purple air has a bunch of data that comes through. It's not just air quality. It's not just one type of air quality. There are several different sizes that it chooses from as far as the particle matter size. It also does temperature, humidity, and a few other metrics. That's a lot of data. So you could do something like principal component analysis, PCA, to reduce all this data down to which one is affecting the output the most. And then take that into consideration for our machine learning. So there's really just so much potential left with this. But honestly, for me, my next steps are to determine better things for the model itself. Because if you go watch the stream anytime, which if you want to, you can view an anonymized version of the stream without having to log in. Okay. There's a bunch of...
Oh yeah, we can put that at a link in the description if you guys want to check that out.
Yep, we can put in there's unanonymized links or unanonymized versions, but those are locked behind a password login that's server side. So we can essentially what we can do is we can go through and optimize this model, because if you watch it and you see this video footage, you'll see that sometimes items get a new ID, or sometimes items don't get detected at all. Like I couldn't even tell you how many cars I've seen pass through these intersections that are clear as day. A car, like there's no. Sometimes you can tell. You get into a feel of, oh yeah, I can see how that could confuse a model. Like one fun thing I used to do back when I was showing people about YOLO and showing them to high school is, okay, it knows cat, it knows dog, it knows horse. Find me a picture of a cat or a dog wearing a horse mask and show it and see what it calls it. And, just give students a fun opportunity to go look on their phone, try to find it, and show it up to the camera and see, oh, what does it see? What does it see? So you kind of get a feel of, oh, yeah, I could see how that would confuse the model. No, it has no excuse. I'm determined that the model only knows things only knows cars and vehicles and people from certain angles that aren't the ones that it's getting from where the cameras are mounted on the poles.
Right.
So I think when it gets in that data, it's like, I've never seen one at that angle. That's not a car.
I'm not fully artificially intelligent.
Right.
We're not quite there yet.
Right, exactly. Machine learning is a subset of artificial intelligence.
Right.
So it's got to get there.
It still has a way to go. But on the subject of that, then we only have... we've got about 4 minutes left. So... you talked about like the potential for this for like traffic and stuff like that, but just outside of that, maybe into the world of science fiction just a little bit.
Sure.
What kind of potential do you see for things like this in the far future?
Well, okay, so imagine you see Tesla talking about cars that can drive themselves and, cars that don't even need a steering wheel anymore. Imagine taking that idea to other things, like a bike share system that doesn't need handlebars and that doesn't need a pay system. It just, you say, here's where I want to go, and it takes you there. You don't have to worry about it, how it gets paid for, or how whatever. It kind of handles its own thing, because let's say the smart city can track the bike all the way throughout your path that you take, and it knows where you started and where you ended. there's a lot of opportunities. They're obviously restricted by our promise to the community of privacy, because things like what I just described wouldn't be possible in our infrastructure, because we'd have to know your face and be able to track you the whole time. But there is a lot of potential for just some really cool, just imagine, if you will, right now we live in a community where when we go downtown we don't really feel connected, in the sense that if I didn't have my phone right now, that's a great way to think of it, is if I don't have my phone right now, how am I going to get around? If I needed to call an Uber, or needed to get a bike, or needed to pick up a cab or whatever, in the future, cabs are going to be dead. They're already dying drastically. Yeah. So if you're stuck where you can only get an Uber with some device, and you don't have a phone with you, imagine if the city could help you with that. If you could have a city where, you have right next to the pedestrian crosswalk buttons, you have the order me an Uber button. You have, these different opportunities throughout the city to help you along your way. Or for you to be able to wake up in the morning and have the city tell you, hey, today's going to be so-and-so kind of day with the weather, and your commute's going to look like this, and your other options of commuting could be through these public transit options.
Just moving towards a more efficient, well-rounded society that takes less effort to function.
Exactly. So that's really, and I can't really think of a lot of ways that some crazy smart future could be, but it can get a little creepy really quick if you're not, if you're not careful. So again, that's why
be very carefully done.
Exactly. That's why our primary promise is, hey, anything we do, we're going to be careful. In fact, we have a data set that we're trying to put together now that is we're going to have to get straight from the cameras from our infrastructure, because we're trying to make a model that's optimized for those angles. Similar to how we have models that can do, they're models optimized for a lot of things that, when you reduce how many things it has to detect, it's a lot quicker, like hot dog, not hot dog. So there are a lot of opportunities for reduction of the data set. Like the YOLO can take a look at things and say up to 80 different objects as to what it would be. So there's like fork, suitcase, train, things that we don't really need. So we're looking to optimize, but how do we do that with this data set that we're trying to build without compromising our promise to say we're not going to save anything? Right. So we're trying to kind of produce a pipeline system where only, certain people who have signed an NDA can contain, can label these objects, and then as soon as they're labeled, they get sent off to the model, and then they're gone forever.
Right.
So it's really complicated, but we're really trying to make it work.
One day at a time, one step at a time.
Exactly.
Heck yeah. Well, I think that's actually perfect, because we have 27 seconds left.
Cool.
So that seems like a really good wrapping up point. Guys, if you like this video, please leave a like down below and leave me a comment. Let me know if you want to see Jose back here again in the future, because I think this stuff is pretty cool. Once again, a lot of it still goes over my head, but I love to, sit down and try and learn as much as I can, because this really is kind of the future we're headed towards. And as always, don't forget to stick around and subscribe for more videos like this in the future. Until the next one, guys. Peace.